Today, we're going to do a lot of little examples, just little ones that are going to make this a little bit more complicated and kind of return to some more algebra steps of this. So, number one, let's go nuts on this. Let's try one like this. The limit is x approaches 0 of x over root x plus 1 minus 1. What's the first thing you try? Yeah, you plug it in and see what you get. So plug this in, and I get 0 over 0. This, I want you to put a little check mark next to that. We're going to learn a technique in the second semester called L'Hopital's rule, which specifically refers to limits where you get 0 over 0. I also want you to write the word indeterminate. That will now be a more appropriate mathematical term than just undefined. And it's going to be because typically when you have 0 over 0, that means that this particular discontinuity is removable. It's just up to you to find an algebraic technique to remove. 1 over 0 is not removable, and we'll have to do other things to get to that kind of limit. So we need an algebra technique on this to try to remove the limit. What? So squaring not only alters the numerator and denominator and makes it not the same thing, but you can't distribute a square across addition, subtraction, and murder the puppies involved in creating that, right? That'd be bad. Give me another one. Yeah. The C word, not the D word. That just got recorded. Okay. X plus 1 minus 1. It's kind of a you had to be here in this class earlier.
That's a good one.
Thanks, Drake.
You're welcome.
Yeah, we're going to multiply by the conjugate. And when you multiply the numerator out, do not actually distribute. You're not helping your cause if you do that. All you want to do is get to a point where you remove one of the factors. The denominator becomes a difference of squares, so x plus 1 minus 1. Please keep writing limit as x approaches 0. I know it's a pain, but it's also mathematically incorrect not to write it on every line. So don't shorthand that. I'm just giving you a little warning now. I don't want to be that person later.
Wait, what if I do it?
Nope. You still need to put the limit on every single step. Okay. So those cancel, and we get plugging 0 in now gives you root 1 plus 1, and I believe root 1 plus 1 is 2. Yeah. Okay, next. Limit as x approaches 2 of x squared plus 5x plus 1 over x minus 2. I'm going to use this problem to accomplish a couple of things. First of all, when you plug it in, what do you notice? You get what? Yeah, I actually reworded it exactly how I'm getting in my brain. You get something that is not 0 divided by 0, right? So we're going to get a version of undefined. We need to figure out a little bit more about what's happening with this, and that's where I want to get you guys a little bit thinking about the graph of this. So we're going to graph that in your brains. Yeah, we're actually going to graph this, and of course you know what this graph looks like. You may not, and that's fine. What we did with rationals, where the degree of the numerator was greater than the degree of the denominator, is the same thing we're going to do in calculus when this happens. We're going to divide this out. And I'm going to divide this in my method. It's fun. When you get to know my method of division, you don't have to write too much else out. So here it is. Here's my method of division. Go with it, enjoy it, or not. I'm going to take the x minus 2 in the denominator. And I'm only going to look at the x squared up here. And I'm going to decide what would I have to add or subtract to x squared to make the x minus 2 cleanly divide out? What other factor would have to hit? Okay, well, it's got a minus. I know I need that. I know I need a 2, but what else do I need on it? X. Does that make, like, x minus 2x would cleanly divide? Now, there is no x minus 2x. If I look up here, I have a 5x. So I just had a negative 2x. What would I have to add to that negative 2x to make it become the 5x? Yes, plus 7x. Same question now. What would I have to add to 7x to make x minus 2 cleanly divide that? Negative 14. But I don't have a negative 14. I have a positive 1. So what do I have to add now to compensate for the minus 14? Plus 15. Rest assured, this is exactly the same result that you get if you do synthetic division or long division. But the reason I'm doing this is because now in my head, I'm going to group this, this, and this. And we're going to end up just dividing this out. Where the first set gives me, okay, so what is x minus 2 divided into x squared minus 2x? X. What is x minus 2 divided into 7x minus 14? 7. And I have the final remainder, 15 over x minus 2. The more you do this, the better you're going to get at that. But I kind of crafted that as a means to not have to completely rewrite the problem just to do the division. And it's fun. It's quite interesting math. So again, if I try plugging in this 2, what I'm going to get is essentially 2 plus 7 plus 15 over 0. What is 15 over 0? Yeah, which is really what? I mean, you shouldn't write this, but you can, but you shouldn't think about it this way, but it really is. It's infinity, right? Remember that number line that I've shown you guys a couple times where on one end you have, or middle you have 1, and on one end you have infinity, and on the other end you have 0. And if you kind of play the reciprocal games where every single number to the right has a reciprocal to the left, and we can mix and match, then eventually we get the idea that 0 to the negative 1 is infinity, and infinity to the negative 1 is 0. Don't ever say that, but it's kind of what's happening. So this is like 9 plus infinity, and 9 plus infinity is, it's not 9. But here's the real issue. Let's get back to this x plus 7 plus 15 over x minus 2. What I want to check is the signs. So we're going to check 1.9. And all I want to know is that when I plug 1.9 in, do I get a positive or negative number? And actually, I really, really, really just want to check it right here. I don't care about the rest of it. That's where the split is happening. What happens is I check 1.9 when I plug it into 15 over x minus 2. Yeah, we get 15 over 1.9 minus 2, which is definitely less than 0. We're also going to check 2.1, which is 15 over 2.1 minus 2. And that's greater than 0. Well, they're right about to the left and the right of 2. If I kind of look at what I'm really doing, the limit as x approaches 2 of all of this, I want to figure out what's happening to the right of 2 and to the left of 2 and see if I'm approaching in the same direction or if I'm approaching the opposite directions. Does that make sense? Yeah. Just I want to see if am I hitting it up in the same place, like a split like this or like this, or are we doing something like this? We're doing that one, clearly. And the graph of this, as a sketch, is going to look like a vertical asymptote at x equals 2. When x is super large and super small, that 15 over x minus 2 doesn't matter at all, because it's going to basically reduce down to 0. So the x plus 7 will matter, and that's going to look like this. And your graph as this little sketch, remember, when we're at 1.9, at x equals 1.9, it's getting really tiny and going negative. Your graph's going to look like that, which I should have drawn it somewhere else. But all that really, really, really matters for this graph from a limit standpoint, let's drag that down. From a limit standpoint is the idea that these are not the same thing. As I'm hitting up x equals 2, a split happens, which is a whole complicated way of saying the limit does not exist. Now, you guys will get better at this. You will get much, much, much better at being able to understand how splits happen around asymptotes. You want the quickest way? The x minus 2 is raised to the first power. And since it's raised to the first power, the split happens. It only will converge to the same side if it's raised to an even power. It's a term that I've coined a double asymptote to kind of copy the double roots or the quadruple roots that we've done. Remember, when you have a double root, that's a turning point. When you have a root to a power that's odd, it crosses over the axis. The same kind of thing happens. If you have a factor that's being raised to an even power, you're going to see that factor in the denominator look kind of like, here's an asymptote. It's going to kind of do something like that, where it approaches from the same side, or from whether it's up or whether it's down. Okay, we will have plenty more practice on graphing. Your homework's all entirely algebra stuff, but I wanted you to see some examples of what happens when you can't remove the discontinuity. Because that's going to be big on this. You're going to spend so much time removing discontinuities that when you hit ones that you can't remove, you need to go to analytic techniques to figure out what's going on. Meaning you need to either look at a graph or do what we did right here, which is plug in numbers just to the right or just to the left of it to get an idea of whether they're blowing up one way or the other. I actually didn't have to check 1.9 or check 2.1. I could have gone with what I know about the graphs. And as we keep going, we're going to kind of remind you guys how to graph these things and what they mean. The fact that this rational function right here, the whole thing, way up here, I can't look at that and know what's going on there. But I can look at this and know what's going on. I can know that that's the graph of a line. That's the line x plus 7. It's x plus 7. If you zoom out sufficiently far, it will look exactly like the line x plus 7. It's only when you get around x equals 2 that it disrupts and gives you a little asymptote going on. Because the closer you get to x equals 2, the more the 15 over x minus 2 takes over. The further you get away from it on either side, the more the x plus 7 takes over. Okay, next, I'm going to scan your homework and see if I really want to hit up the trig ones right now. I don't think I do. 43 through 60 doesn't have them. But 43 through 60 does have an interesting problem. And I'm going to cheat right now and do 43 with you so you can get a sense of how these directions work. This is a direction, oh no, we do want to do the trig ones. Oh, sweet. It's okay, we got 10. So let's do 43. So I'll split screen this and kind of talk about 43 here. It's okay. You can copy them down in your notes, and then we'll do 40. Just start with 44. It'll be fine. I'm not going to take, some of you guys are so compulsive that you like, what's funny about these? Okay. Let's look at the directions for 43. It asks, find the limit as x approaches c of the average rate of change of each function from c to x. C equals 2, and f of x is equal to 5x minus 3. And it says, find the limit as x approaches c of the average rate of change of each function from c to x. The average rate of change of each function from c to x. What is average rate of change? Yeah, slope. So from c to x, that means we're going to do f of x minus f of c over x minus c. Doesn't that look a little familiar? No, do you remember that thing called a difference quotient? Oh, yes. Well, let's do this. So f of x is just going to be 5x minus 3. And f of c is 5 times c minus 3 over x minus c, limit as x approaches c. What happens to your 3's? The 2 for c. Oh, we're going to do that in a bit here. Yeah, you can do it here. That's fine. If you want to say, I'm so calculus in my head that I know it actually doesn't matter what c is in this problem. But we'll do it. In other problems it will. Limit as x approaches 2 of 5x minus 5 times 2. over x minus 2. Take out a 5, I get an x minus 2 over x minus 2. Cancel the 2's, and the limit is equal to 5. And maybe right up here you can see that it actually didn't matter at all what c was equal to, because x minus c was going to cancel anyway. In a later problem it will, so that's okay. Guess what that is actually called? You might. It's the entire first third of calculus. That's the second third.
A derivative?
Yes. This is called the derivative at x equals 2. It's the slope of the tangent line at x equals 2. And the slope of the tangent line of a line itself is its slope, so that's why it's like, okay. So that's a problem type you guys are going to encounter. Let's kind of skip ahead to another problem type. So that was 43 in your book, but then we'll just kind of go back to number 3, because why not go out of order? And this is also at the top of the next set of directions, and I want you guys to take a look at these things, these facts that it gives you. And it gives you these without proving them, which is sort of where we start, because the proofs of these will come later. I'm going to put a little, wait to put number 3, and just write down a couple of things. I'm going to give you guys that the limit as x approaches 0 of the sine of x over x is equal to 1. And it's a limit reason we'll get to later, but we get to do a lot of manipulations with this basic fact here. The limit as x approaches 0 of the sine of x or over x is equal to 1. So I want to kind of branch upon that and show you that you can do a couple of limits with that knowledge. For instance, you can do the limit as x approaches 0 of x over the sine of x. How, per se? X over the sine of x is nothing more than the limit as x approaches 0 of the sine of x over x raised to the negative 1. And at the moment that you have the sine of x over x, and the moment that you are approaching 0, we get to say that that's 1 to the negative 1, which is also 1. Yeah. This is one you guys are going to want to know and memorize, because we're going to use that one a lot. I'll even keep that up and do number 4 right next to it so we can keep this going. The limit as x approaches 0 of the sine of 3x over x. What I want to do is get a pattern where I have the sine of something over that same something. How can I make the denominator be the same as the argument of sine? I need a 3x, so what can I do? Yeah, multiply this by 3, but then to compensate, I would have to multiply the numerator by 3. Now, you have the sine of 3x over 3x, and when you plug in 0 for x, that's the same as the sine of 0 over 0, which we just said, based on the property right here, is 1. This now is the same thing as 3 times the limit as x approaches 0 of the sine of 3x over 3x, which when the pen is not freezing, okay, there we go, operates the same way, or operates exactly the same way as the sine of x over x, because x is approaching 0. This whole thing is 1, and that gives you a limit of 3. Do another. Limit as x approaches 0 of the tangent of x over x. Do you see a sine x over x buried in there? One that you can pull out, because that's what your goal is. You're trying to find a sine x over x. What is tangent equal to? So if I go sine of x over x times 1 over cosine x, I'm splitting up the tangent into sine over cosine. We're approaching 0. This is 1, yep, times And always try direct substitution. What is 1 over the cosine of 0? 1. Limit as x approaches pi of the sine of 7x over x. What's this equal to? If this were x approaching 0, which it is not, I'd be looking for that sine x over x. But x is not approaching 0, x is approaching pi. Go back and try direct substitution. We had to do funky things because we were dividing by 0 with the x approaching 0. Are we dividing by 0 here? If I substitute it directly in, I get the sine of 7 pi over pi. What is the sine of 7 pi? Yeah. Sine of pi, which is 0. Because at pi and at 0, there is no y value. That's on the x-axis. So this is 0 over pi, and 0 over pi is 0. That's proper 0. That's good 0. Okay. I'm going to choose to stop there. And we'll throw this up.